from the Transplant Operations Institute.
Okay, I think we have waited for 4 minutes beyond 11. We will start, shall we? Yes. Yeah. Okay. So good morning, everyone who is attending this meeting. It's a pleasure to invite all of you and all my senior colleagues at IIIT Hyderabad and the Innovation Hub at IIIT Hyderabad, especially on a Sunday morning. Welcome you all. I now request Professor Devapriya Kumar, who is the academic head of the Innovation Hub, to preside over this very short session for the launch of the much awaited Foundations of Modern Machine Learning course. Professor Deva.
Yeah, so thank you, Professor Gopalakrishnan. So, first of all, I would like to, take, a lot of pleasure in welcoming all the, the first batch of the students of the Foundations of Modern Machine Learning course, which is being organized by IHub-Data at IIIT Hyderabad. Right, so, one of the, this is something that Professor Jawahar put a lot of thought and effort into planning this course initially, and then of course later the whole team, Professor Anup, Dr. Raju, Professor Gopalakrishnan, Dr. Ravi Kiran, and all of them spent a lot of time in the last almost a year now to bring this to reality, and then we are starting today. Right, so I will maybe take 2 minutes, and then I will request Professor Vijay Narayanan to say some few words. So one of the maybe initially just to talk a little bit about the IHub-Data. This is a technology innovation hub which is established to take up research activities and in the area of data-driven technologies. It could be data. Collection of data all the way up to developing technologies and productization and so on. So one of the activities that we want to actively take up is to engage with students from other colleges, institutes, universities, and so on, and then be part of their learning, and then do as much as possible from our side to develop the skills, right? Because people talk about new jobs that are being created in the space of data-driven technologies every single day, and at the same time, people speak about serious lack of like competent engineers, right? So, and of course, we also should have a large number of researchers who will be taking up research in this activity. So that way, of course, the MOOCs or online lectures material are kind of bridging this gap. But one of the things that we have been planning is to see if we can make the learning much more personalized, but at the same time be able to do sitting in multiple places within the country. So that way, I think this course is going to make a huge difference in terms of training more people, and possibly having you in our further plans, or taking up jobs, or taking up research in this particular area. So with that, just quick words, I would like to request Professor P.J. Narayanan, who is the director of IIIT Hyderabad, and he's also the chairman of the governing board of IHub-Data, the technology innovation hub. Right. So Professor Narayanan has spearheaded many initiatives at IIIT Hyderabad centered around such disruptive technologies, maybe AML or blockchain or quantum computing recently, and so on. Right. So IHub-Data is one of many such things that is happening at IIIT. So with that very short, introduction, I would like to request Professor P.J. Narayanan to say a few words.
Thank you. Thanks, Deva and Gopal, and welcome to all the participants. I understand there are about 300 of them, and I'm impressed to know they have come from the one end, the west end, and the right, east end, the south end, and the north end of the country. And that was exactly our wish. So IIIT Hyderabad has been a research-focused university. It's been around for now 23 years. But from very beginning, we were strong in so-called AI areas, natural language processing, computer vision, data science, robotics, and other associated areas. And our students, both the BTech, Masters, and PhD students, get very well trained in different aspects of AI. And they go on to become big leaders all over the world. That has been happening. And this the technology enabled data-driven technology missions of this, all the TIH, these skill development in their area, in the hub's area of expertise. How do you have large-scale skill development? I mean, IIIT teaches its students AI in different forms, but that is, we get 300 undergraduate students per year. We get, a few PhD students and few master students per year. How can we do it at much larger scale? This was the thought, and we have been engaging with, entities or students or participant outside of the traditional academic entity for academic institution for the last 4 years at least. We started a large-scale executive education program in AI ML first, then extended it to blockchain and software engineering, and then another one in IoT is starting now. So we do have experience, and we have also engaged with local engineering colleges and students on small-scale efforts in the past. So here is an idea of putting it all together, our expertise in broader AI or machine learning or modern machine learning, with our experience in reaching out to sections of the society outside of the traditional academic, our students on our campus. And the vehicle or the impetus is given by this TIH or the IHub-Data, which is expecting it, and we have funding and other support from it. So it's all these factors coming together. That's how this is announced. Our team has put in a lot of effort and thought, as Deva mentioned, and I'm sure the course will be very useful to every one of you. And it's a long, it's a year-long course. And don't think this will be just listening to lectures and then thinking about it. You will be doing do some labs, do some assignments, and required support will be. And face it, the more effort you put into it, the more you will get out of it. So I implore you, I tell every one of you to put as much effort into it as you can afford. Think deeply. Go look at the theory aspects. Not just getting some program working these days. Getting some program working in this area is kind of easy because you're all, you are all people who are seeking knowledge. You are not just toolsmen. You want to be researchers someday. So we would expect you to put in as much time and get as much out of it. Bother our students and faculty members with questions and doubts when you have them throughout the semester or throughout this year-long program, and get maximum out of it. Once again, I welcome all of you to this event, and I thank the organizers, Deva, Gopal, Jawahar, Anup, and Ravi and team for organizing it. I'm looking forward to very productive engagement with students from far and wide. Thank you.
Thank you, Professor Pijanaran. And so, so thank you for your kind words. So now I would like to request Professor C.V. Jawahar to say a few words. Just to quickly introduce, Professor C.V. Jawahar wears multiple hats. So, he's our, Dean of Research and Development at IIIT Hyderabad. He's a well-known, well-respected researcher in the area of, AI/ML internationally. And, as I said, he's the one who, kind of conceptualized this course, the way of doing this course initially, and before involvement from others like me and Professor Gopal and so on. And then, he also, heads the mobility related areas in IHub-Data. So he's, leading that effort, in smart mobility using AI/ML data-driven technologies for making the roads, or specifically Indian roads, safer and so on. Right. So with that very short introduction, I would like to welcome Professor C.V. Jawahar, please.
Thank you, Deva and others. Introduction, as well as good to see this program now taking off. So I just want to take a couple of minutes to tell you some background history which some of you may not know. So today, what we know is the AI machine learning is the thing that is happening everywhere, and or whatever today AI we call is primarily machine learning and machine learning driven things at this moment, and mostly, to be precise, a little bit more of deep learning. But we know that there are a few more very deeper issues, or maybe let me go back in the history a little bit. So this community of machine learning has a little bit interesting history that you may want to know. So this is a community that has strongly argued and worked towards open knowledge, open resources, and democratizing knowledge. So if you want to go some of the previous examples, so this possibly the top set of researchers had at some stage fought against the big publishers and broke away creating journals which are not paid journals or published journals, or require open access with free publishing schemes. This is a community that over time took a lot of effort in creating open libraries, releasing softwares, and pushing a number of open resource projects in the high-tech areas. Far more, the first set of open courses is what we call about today as MOOCs, were all in the area of AI, machine learning, driven by the pioneers in this space, which some of you may still remember the initial courses from on robotics, AI, machine learning, from top people, which eventually led to the starting of Coursera's and other things that happened. So a lot of open knowledge for learning in machine learning. But when we, now let me try to contrast with the other end of the spectrum. When I would like to hire a student to work on a project related to machine learning, I don't find the right candidate. When I talk to my industry collaborators about, they immediately ask you, do you have a student who is trained in machine learning? So they don't have access to the right set of people. So what went wrong? On one hand, we have like an open knowledge, open resources, plenty of courses in this space. On the other hand, we are struggling to have the right set of people to get into like a development, research, whatever technology development, whatever you may call, to work in the broad area of machine learning and the applications. So we realize that there is a small gap in between. This is the gap that gets filled when you take a formal course with proper or deep mentorship. So we say today, unfortunately, even in some of the recent programs that I organize, I see people asking the question, can you please give me the slides? This was the story earlier. Like, if you give me the slides, that was everything. A set of students always ask that if you give me the slides, I can learn everything from them. Now the slogan has slightly changed. If you give me the videos, that is enough for me to learn. Remember, that is not enough. And that is what a number of courses have done till today. And that you need to go one level further. If you really want to understand and go deeper, you need to have a mentorship. There are, say for example, I tell jokingly saying that, look, if a student has to get a machine learning model working, you have to train 100 times. It's a question of how fast you can finish your 99 failed attempt is a question. So if you want to do this today, so you need a different way of learning, particularly in machine learning and today's AI, which is highly an empirical science. So when we were designing this course, we were asking this question, what can we do so that we can do this at scale? So this is not possible very easily. So if you want to have a scalable course with also a deep mentorship, is not very easy. And we were wondering what is a scale at which we can go, and how do we make that happen with limited resources that we all may have. And that is what resulted in this course, where we hope that we would like to reach out to a large number of students across the country from different colleges who are deprived of teaching and practical training in their respective colleges for various reasons, but bright students. We would like to see how we can share our experiences. Not just the a quote unquote slides and videos. They are easy. I can just give you the links for plenty of exceptionally good slides and videos and textbooks. It is not the lack of that stopped you from learning or becoming a machine learning expert or a practitioner. There is something more. And that is what we would like this course to give. Now, how do we do that? So one thought we had is we would like to have a theory and practice, and far more a direct contact with the instructors and TAs who are humans. So these are not chatbots who are answering your queries automatically. These are humans. You should be able to talk to them. And how do we enable that in an online mode? Maybe sessions, parallel sessions, say discussion rooms, office hours, and the laboratories with teachers. So we all have learned a lot from teachers and TAs and tutors who come to our lab and tell from them. So this practical skill we learn from by doing it and in front of mentors than reading the textbook. You never learn swimming by reading the textbook. You never learn cycling by reading a textbook. So you can learn the basics of what to do, but you really need to get into that. You may fall down, you may get hurt. It is okay. You have to get up and walk and proceed. And we are there with you to support you. And that is what we hope this course will be able to provide you. So this course has lectures and laboratories, of course, quizzes, practicals, extensions, projects, a number of things. Which from a pedagogy point of view, we also thought that we would like to connect this not as a textbook course, which possibly starts with lot of dry theory equations, and eventually at the end of the course you start to see some applications. We would like to weave the applications, the possibilities from quite early, and see how the learned ideas you can apply. And also, we understand there may be students with different levels of background, different levels of interest or expertise or commitments at this stage. So how, and possibly people with variable speed of learning, how they can be all adjusted in an online mode. We have thought about that and tried to do some of these aspects into the design. So the course is generally designed as a set of modules, so that each module has a more or less self-contained, there's a big project team, a set of exercises, a set of concepts. So this is how we have tried to build the module, with a lot of input from my colleagues, as well as a lot of input from the TAs who have been working very actively with us for the last few months.
Hello, hi sir.
So they have put a lot of effort, given a lot of feedback on what to do, what not to do, and which portions will be tougher for students to digest, and how do you sequence them, how do you arrange them, what type of motivating examples will be good. So we have a lot of inputs, and we also look for input from you for further improvement. And we expect you to continuously participate in this course, not just as a passive student, but as an active learner and player in this learn. So this is a story of active learning. So you need to know, you cannot learn you don't want to learn as a passive listener. So that is not the way to take this course. So this course also looks for, so now we also have some thoughts on how do we take this forward. So not just the getting a certificate or getting a mark in this course is the goal. So if the students who are doing very well in this course, we would like to surely get them on campus in whatever form that is possible. So we will have appropriate programs which can host you on campus, and for a sufficiently long period, depending, maybe summer, maybe a semester, depending on whether your university or university will allow you. And then maybe work on projects. So there are many other mechanisms of connecting you closer to institutions like ours, and maybe other institutions too we are working on. So this is something that we will see as we move forward, how do we make it happen. Particularly the pandemic possibly has exposed us to do things in a very different way, good and bad. We had seen of this digital learning and research and projects. Okay. So look forward for a continuous association with all of you. That's all at this stage. Thank you.
Yeah, so thank you very much, Professor Jawahar. So again, I would like to take this opportunity again to welcome all the students who have enrolled in this course, and we sincerely hope that as Professor Jawahar mentioned, please engage with the coordinators, professors, TAs, and so on, and then gain as much as possible from this particular exercise. So I wish all of you good luck, and thank you again, Professor PJ and Professor Jawahar. I give it back to Professor Gopalakrishnan now. Thank you very much.
Thank you, Professor Deva, for nicely conducting the session. So now I invite Ms. Trupti and John to propose a vote of thanks.
Thank you. On behalf of IHub and all present here, I thank our director, Professor PJ Narayan, for launching the FMML course. And I also thank Professor Devakumar for his words and all the help he has extended to make this program successful. And I thank Professor C.V. Jawahar, the Dean of Research, for sharing his insights on the background and the concepts behind this course. And we gratefully acknowledge all the help received from the staff at IHub and IIIT, as well as the students and members of faculty at various stages during the planning of this course. And last but not least, this event would be meaningless without all the participants who have joined from various regions of the country. I thank all of you for being here today, and I wish you all an exciting year of learning and practice with this course. So with this, we have come to the end of this inaugural session and the first lecture of the FMML program on Introduction to Modern Machine Learning by Professor Anup Nambudri will start shortly. All participants of the program are requested to stay back. So thank you, sir. Back to you.
Thank you. Thank you.
Thank you.
Okay, good. So now that the program is formally inaugurated, we will get started. Since we said 11:30, we will start at 11:30. So let's wait for maybe 3 minutes, 2 minutes more, I guess. So after that, we'll get started with the course. By the way, am I audible? Is there any?
Audible.
Okay, good. Yeah, let me just share my slides. I hope that is visible now.
Yes.
Okay, so we have a couple of minutes. After that, we'll get started. Okay, let's get started then. It's 11:30 already. So today's lecture is expected to be roughly, 1 hour, 15 minutes, at most an hour and a half. So we will definitely stop by 1 o'clock. So before we get started, a few points I want to mention that this course is actually a pretty as you can imagine, the number of participants is quite large in the classroom sessions. The lab sessions and the one-on-one mentor sessions will be in a smaller groups or one-to-one. However, the classrooms are going to be relatively large, and we will use slightly different kind of mode. So today we are, as an introduction, we are starting it as live teaching. In other cases, we might actually play a short video that we record and then discuss on top of it. And we will have definitely breaks in between where you can ask questions. Okay. I would really love you to ask questions whenever possible. However, if you start asking questions in every single slide, then we won't progress much. So if you have a question, definitely do ask, but hold it in your mind for a few minutes. See if that question is answered in the next slide or the next line that I speak. Usually it is, because when a doubt comes to your mind, usually that doubt might be answered soon. If not, if you don't see the answer to it in a next slide, you can definitely ask me the question, and we will be happy to answer. We want to be able to complete the lectures on time. That is definitely one aspect that I wanted to talk to you regarding the class etiquettes. So hold your questions for a short period of time, and then if you don't get the answer, please do ask. Second, keep your microphones and cameras muted during the class unless you want to speak, so that there is no disturbance in between when we are conducting the class. And the next point is slightly larger. It is a generic comment that if you want to be able to learn anything, in fact, specifically something like machine learning, it is extremely important that you actually do a hands-on effort to learn. You cannot learn this as a spectator sport. You cannot stand in the gallery and learn machine learning. That doesn't happen. Okay, I think Professor PJN talked about it. Jawahar talked about it. The idea is that unless you do things, you will not learn how to do. And you will not be comfortable in learning. And in several cases, the style of applying machine learning is significantly different from most of the other things that you've learned, specifically programming and all the structured problem solving skills that you've acquired. Machine learning is different from that. So in that sense, there is one fundamental paradigm shift from traditional styles of problem solving and a machine learning based style of problem solving. So because of that, it is important that you absorb that difference. There is some amount of shift in your mindset that has to happen. And whenever a shift in mind is required, it's not easy. Okay, it's human nature that our brain will really vehemently object against any kind of significant changes in understanding that you want to make. And this is part and parcel of the reason why machine learning has not, as Jawahar said, hasn't taken off, in spite of the fact that there's so much of material and videos and resources and everything available. It hasn't taken off because it requires effort from the learners. It is not something you can just watch a video and understand. It takes effort. Okay, and it hurts in the brain. It hurts when you try to change your thought process. Okay, it's part of our makeup. So be ready for that. Learn to think differently and be able to apply your knowledge, and you will do well by the end of it. So that's all what I wanted to say as an introduction. Now let's get into machine learning. So today is primarily an introduction, a few simple concepts I'll talk about, which is going to be the basis on which we'll build up other things. And we will have some lab sessions following this one today and later in the week. So let's start with asking the question, what is this learning? Okay. When we say learning, what really happens? Both in the case of human learning and machine learning. We will start with machine learning and then we'll try to connect with human learning. Okay. So let me start with a couple of questions. Here, I would like you to respond. Okay. You can respond by typing in the chat. If you think that somebody has answered and you want to say the same answer, maybe upvote it so that things are easy. And again, if you are answering, please don't directly message me because I want others also to be able to see it. Okay, so this is more of a classroom discussion. So let everybody hear it. What is the next one? Of course, I think a few people have directly messaged me, but yeah, I think most of you got it. It's just simple 2468. Okay, so the next most likely answer in the sequence would be 8. That's fine. Okay, easy one. Next, 357. What is the next one? Okay, 9. Sure. Why not 11? Is 11 a correct answer? So Sai Kanish says it's not a correct answer. Why not? If you think of 357 as odd numbers, yes, the next one in the sequence should be 9. But if you think of 357 as a sequence of consecutive prime numbers, then if you get 357, the next one in the series would be 11. Okay. So now here is an example where you get a sequence and the next number that you predict, there are 2 valid answers. There is no single correct answer. There are 2 different answers. Both are correct. It depends on what is your underlying assumption. Is this a sequence of odd numbers or is it the sequence of prime numbers? Depending on that, things would change. Okay. Let's see. 2358.
Excuse me, sir.
Yes,
I think the chat box is not enabled for all the participants.
Oh, I see a whole bunch of people responding to me on chat, but everybody is only sending direct messages to me, not for everyone.
Yes, I think that's not.
Okay, that's fine. That's fine. So you can direct message me also. That's fine. So several of you gave answers. I see both 12 and 13 as coming as answers. What would be the reason? So what is the sequence?
2 plus 1, 3, 3 plus 2, 5, 5 plus 3, 8, 8 plus 4, 12. 12.
That's one way to think. So you had 2 to 3, it's a difference of 1. 3 to 5 is a difference of 2. 5 to 3, 8 is a difference of 3. And 8 to 12 would be one possibility. Or it could be 13 as well. Okay. Why is it 13?
Adding up previous 2 numbers.
Fibonacci series generation.
If it's Fibonacci series, then 2 plus 3 is 5. 5 plus 3 is 8. 8 plus 5 is 13. Okay. So that is another possible answer. Okay. So there are several possible answers like that. And some of them, some of them may be fitting at the beginning. You say, okay, 3, twice of 2 is 4, minus 1 is 3. Twice of 3 is 6, minus 1 is 5. Twice of 5 is 10, minus 1 would be 9. So you might see different things fitting, but at some point they are different. In this particular case, again, you have 2 different answers. You could have either 12 or 13. If you think of progression where the differences are in arithmetic sequence, then it would have been 12. But in this case, if you think of it as a Fibonacci series, then it would be 13. How about this one? Any guesses? Suddenly it gets more and more difficult, of course. I don't get an immediate answer. If you think a little bit harder, maybe you might get to the answer, but that's not the point. It's not immediately obvious. The other 3, many of you could guess it quickly, but this may not be as easy. Okay, because what I really did is I did square the previous number and subtracted 1. So 2 cubed minus 8 and stuff like that. So sorry, what was it? I had put some model there. Okay, I'll do. I need to recheck what I did, but there was a sequence that I had thought about, a simple equation, and then I think it was x squared plus x or something. Okay, some simple equation I had built up, and that would result in it. So now let's look at what did we do. Yeah, it's x squared plus x. So even I couldn't recollect immediately. My point is that x squared plus itself it's not such a difficult function, but it's not so obvious to us. So let's kind of think out what is our mental process when we are actually trying to solve this. Okay, so you see a data sequence. Let's call the sequence as x. X is a vector maybe with a sequence there. And in your mind, you have models. You think of odd numbers, even numbers, squares, cubes, prime numbers, Fibonacci, standard sequences that you've seen. There are many of them. In many of these things, what you really do is you have these different sequences or patterns, if you want to call it, in your brain that are the models box that I have drawn there, and the sequence of numbers that you've seen. You kind of try to do some kind of a matching between these two. Okay, you try to match the kind of models or sequences or patterns that you have in your mind with the numbers that you have, and out pops some kind of a model saying that, oh, this particular model, in this case, x squared plus x or x squared plus x plus 1, whatever that model is, that fits this one well. Okay, so based on that, you notice that there is certain pattern there, and then what you do, this is the initial pattern matching sequence. You're trying to find the best pattern that matches. Once it clicks, yeah, now I know what the sequence is. Once you have simplified the series of numbers into a mathematical model, like odd numbers is a mathematical model, even numbers is a mathematical model, prime numbers is a mathematical model, Fibonacci sequence is a mathematical model. Okay, so once you've done that, then all you need to do is, okay, if that is the sequence, then you just take the sequence, plug it into this model, and out comes the answer, that the prediction that you want to make. And this prediction that you make is usually referred to as, that we call it as Y. Okay, so Y is the symbol that indicates the output. You have a sequence of numbers, X is the input, and out comes Y, but in between there are two things going on. One is from your library of models that you have in your brain, you do a matching and then find out the best fitting model. For some people, the order in which you retrieved those patterns from your mind was different. For somebody, it looked like Fibonacci sequence. For somebody else, it looked like it is, number B, the incremental difference between the two numbers are incremented by 1. So that different kind of models would fit the same sequence. Okay, and you would make a slightly different prediction based on that. So this is natural. Okay, and why are we saying all the story? Because this process is very, very similar to what we do in machine learning. Okay, so that's why we wanted to spend some time on this particular model. Now the question is, can you write a program for where a machine can do this? If you can write a program to do this, then you have done your first example of machine learning. You are actually making a machine capable of learning from a sequence of data and then using that to make predictions. Okay, it will look at a set of numbers, learn what is going on there, and then based on that learning, it would make a prediction. Okay, this is what was happening in your brain, and that is same thing that would happen in the case of a machine learning algorithm. But how to go about it, we will get to it in a more detailed fashion. Let's look at a very similar second problem. What you're given is a bunch of pairs of numbers, 3:5, 1:1, 5:9, -2 to -5. Okay, these mappings are given to you. Now the question is, what is 4 related to? Okay, or what is -1 related to? How do we go about solving this problem? Okay, it's very similar to the previous one. It's not a sequence that is given, it's a set of pairs. The order doesn't matter. Okay, 3:5 is one pair, 1:1 is second pair, 5:9 is another pair, and so on and so forth. So we don't know what order it is. The order doesn't matter between the pairs, but within a pair, that is the mapping. So 3 maps to 5, 1 maps to 1, 5 maps to 9, -2 maps to -5, and so on and so forth. Okay. So how do we do this? Yeah, one way to do it is to think of these pairs as points in a 2D space. So you plot these points in a 2D space. Think of the first one as X and the second one as Y. You have 3, 5 is a point in there. 1, 1 is a point in there. 5, 9 is a point in there. And -2, -5 is a point in there. Once you have these, then you ask the question, what is the relationship between all this? What is a simple model that fits everything? Okay. Same idea that we talked about before. Earlier, the models were this kind of sequences, odd numbers, even numbers, Fibonacci, and so on and so forth. Here, the model is more of a physical model. You're thinking about this is some kind of a relationship between them. It looks like in the 1 dimension, the 2 dimensions, this almost looks like a line, a straight line. So we can draw a straight line through it. And as I think Azam has already pointed out to you, Azam, I guess, if I pronounce your name wrong, please forgive me. Okay, that's maybe I'll try to get it right over a period of time, but yeah, let's see. So y equal to 2x minus 1 is a simple relationship, and this is fine. So once I have that relationship established, I have fitted a model to the data. And once I have the fitted model, I can make any prediction now. Now, what is 4 corresponding to? 4 corresponds to 7 here. And what does -1 corresponds to? -1 corresponds to -3, because I know the model is 2x minus 1. Okay. Once again, the question is, how did we solve it? Did we plot this and do it? Maybe we did it. We can, by plotting it, I can just look at it and see that pattern, a linear pattern there, because our brain is kind of evolved to see linear patterns. It's very easy for us to see linear patterns. Okay. But how do we make a machine to do this? Okay. We have already talked about some of the methods. If you know that it's a linear model, then there are ways to solve it. Okay. So we'll get to that. So this is again a second problem. In both cases, what you had is a bunch of numbers and there is one prediction to be made. And here the input was in pairs, and that is what is used to learn the model. And then later on, you're asked one element of a pair, and then you're asked to predict the corresponding matching number. Okay. Now, how can this be difficult? If it's a linear model, you know that, okay, there exists a set of linear equations. You just solve it and you will get the values of X and Y, and you can fit the line to it and you can solve it. Great. But in practice, things may not be this easy. If you have been given these numbers instead of the previous one, like earlier slide, we had these numbers 3, 5, 1, 1, 5, 9 given, and you could probably guess 2x minus 1. That is possible. But if these were the numbers given, it's not so obvious to you. Okay. You may not, it's only minor changes from the previous numbers. But when the numbers are presented in this manner, it may not look so easy. And the same question being asked, what is 4 corresponding to and -1 corresponding to? May not be so easy to answer. Okay. So it becomes more difficult for human beings. But if you think about what machines can do, for machines, it may not be that different. Okay. So the point is that if you look over these things, the points are almost on a straight line. You can still draw a straight line through that. If you can try to find the line that best approximates this set of points, you might get something like 2.03x minus 0.97 is what the most appropriate one. I'm just writing something that is very close. Okay. This is not really that I have solved the problem and wrote it. It is just a rough guess of what that equation of the line is. And then if you substitute your questions, 4 outcomes, instead of 7, it would be 7.15. And if you put -1, it happens to be -3. So you will get those numbers there. Fine. So you can make this prediction still. It's just that the input data is a little noisy. And the method that is used to fit your linear model with the set of data points has to be slightly different. Please keep your microphones muted. So that is the second aspect. Now, the third aspect of it, why can this be difficult? This problem of learning this mapping from input to output. That is what we are kind of repeatedly seeing, that there is some input data X and it is being mapped to Y, and you are somehow learning this relationship between Y and X, Y equal to 2X minus 1 or Y equal to whatever, okay, equation that you have, X squared, 2X squared minus 1, whatever, some equation is there, and that you're trying to learn, okay, from not being told the equation, but being shown a set of examples that fits that equation is the point. Now, one of the complexity that we saw was that the data could be noisy, and that would make the process of estimation of this model difficult. Second is X need not be a simple number. Okay, for example, what if X being, instead of a single number, what if X itself is a 2D point? So XY mapping, X is a 2D point, a two-dimensional entity, and Y is a number. Okay, so if you try to plot this on X, Y, Z, you will see that every point is a point in a three-dimensional space. So think of this picture as in 3 dimensions, and I have put those points as small cubelets, and as you move further away into Y, the color goes from yellow to red. So you see that it's moving deeper into the Y space. So you can think of these as points and the corresponding Y value. So now if you have these points, now what would be the equation? The X itself is not just a simple X, but X1, X2. X is a vector. And in the course throughout, mostly we'll be following this convention that if X is bolded, then it means it's a vector, and Y is not bold. So that is a scalar or single number. Okay. So 2D number is a possibility, but nobody says that 2D is the only thing that is possible. You can have, let's say, 100-dimensional vector. Okay. The numbers need not be integers. It could be actually real numbers, positive, negative, all that. So you can have a long vector. So you can't even now plot it and see beyond 3 dimensions. It's humanly impossible to visualize in D-dimensional plot. You can't think of it. So that's one issue. So 100-dimensional vector is not so easy to deal with, but mathematically it's not any different than 2 dimensions. If you develop mathematical models and algorithms that work for models of 2 dimensions, the same algorithms would work for 100 dimensions as well. So that's the advantage of doing linear algebra, which we actually did quite a lot. If you want to fit linear models, linear algebra could be used. What if the entries are numbers and entities other than numbers? Let's say I'm describing a car, and some of the attributes of that car are, let's say, 3.9 meters long, 8.2 lakhs is rupees as its cost, blue colored sedan is the style of the car. Now, how do I even think of it as a point in a 3D space or 4D space here? Difficult to even imagine, because these entities are not even numbers. Now what do? Can you still deal with entities which are non-numbers? That's a question. And we will figure out ways to solve that. Okay. What if the entry is a picture, not a textual input? Now what happens? You need to be able to represent things within this as well. Or let's say a sound bite. Now you have some sequence of some waveform for the sound. Now what do? All the algorithms and techniques that we develop are based on the assumptions that the input is a vector, a number, a sequence of numbers, or a set of numbers as a vector. So we assume that X is the input and Y is the output. X is a vector of numbers, Y is a single number, number that is to be predicted. Okay, that's the assumption. But these other things don't fit it. Yeah, good with 1D points, 2D points, and even 100D vectors are fine with our model. But the moment it goes other than D-dimensional vectors, like other than numbers or pictures, sound, and stuff like that, we can't do anything now. It's beyond our ability. So how do we deal with it? Okay, so that's a question. So let's just look at how we deal with it. Let's say we are given 2 sets of examples here, cats and dogs. On the left side, you have cats. On the right side, you have dogs. And you're asked to learn the difference between these two. or in some sense, I'm asking, given a single picture, including the picture that you just show. So given this picture, can you say whether it's a cat or a dog? Okay, so the input X is not a vector, it's a picture. Output is cat or dog. Okay, output is also not a number right now, is either cat or a dog. That's fine. But how do you do it? If you are supposed to learn the difference between a cat and a dog, you look at all these pictures of animals and you say that, okay, every picture is either a cat or a dog. And on this training examples, these are given to you for learning. On the left side, everything is a cat. On the right side, everything is a dog. If that is the case, how do you decide? Can you learn how to differentiate between a cat and a dog? Yes, most of us can do. Question is, what aspect of the cat or dog are you looking at to figure out whether it's a cat or a dog? So if you are looking at these ones and given to you as examples afterwards, some of these are actually pictures from the previous one. Let's assume that these pictures are never seen before. These are pictures that you have never seen before. Can you figure out each one is a cat or a dog? Okay, so some of you are giving me some answers. You say that you can look at some kind of features, some properties of these animals. So by looking at things like ears, well, you can say things with pointed ears are cats, but then you also see some of the dogs which have pointed ears. Okay, on the second row, first one is a dog, which is also got pointed ears. And you'll also see, let's say the second row, fourth one is a cat, but it does not have pointed ears. So there are examples. Whatever we give an example, you probably can find a picture where it doesn't fit and it would still be a cat or a dog. Okay, so it's a tricky one. And somebody says distance between eyes, nose, and face. That might be one possibility. Okay, that's not definitely what we do. Okay, so Prachi says whiskers of a cat. That's a good answer. Only cat have got whiskers. Dogs do not have whiskers. The problem is that given the picture, how do you figure out whether in the picture there is whiskers or not? In many of these pictures, whiskers are not visible. For example, if you look at the first row, third one, or the fourth one, these are cats. They are supposed to have whiskers, but it's not visible clearly in the picture. Okay, so then I'm getting answers like, shape of the face, shape of the ears, the shape of the snout, and things like that. The problem is that you are trying to create a solution to this problem of deciding whether something is a cat or a dog. And what you're saying is, to decide whether something is a cat or a dog, you go back and look at things like whiskers, whether the ears are pointed, what is the shape of the snout. The moment you say whether are there any whiskers in it, now you've defined a new problem. The new problem is, how do you identify where the whiskers should be? And if you identified where the whiskers should be, are there whiskers in the picture or not? And there is this famous saying that I believe this comes from Vapnik, who is one of the leaders in machine learning. He said that to solve a problem, do not try to create a sub-problem which is even more difficult to solve than the original problem itself. And we often do that. I want to solve the problem to decide whether it's a cat or a dog. That is a simple enough problem. Okay. But to solve that problem, now I created a problem of whisker detection, which is actually even more difficult than deciding whether something is a cat or a dog. This is the problem. And this we often do, because for us, some problems are easy. Certain solutions are easy to come by, but for machines, it's not. Okay. Yeah. Pupil of the eye, everything has got positives and negatives. In some cases, you may not be able to see the pupil. So that then what do you do? So question is, can you decide whether something is a cat or a dog? The issue is that there is too much information in the raw data. The image is a raw data and it has got too much information. Okay. And whatever is the information that is relevant to us, which is needed for classification, deciding between cats or dogs, is somewhere hidden inside. And you need to extract it out of the image. So this feature extraction is the process of extracting this useful information X, which is the sequence set of numbers that we talked about. So we need to basically pull out a bunch of numbers from inside this picture somehow, so that you will form that vector X, and the mapping from vector X to Y becomes easy. Okay, Y is either cat or a dog in this case. Fine. So again, that is one issue. That the first problem that we talked about is the numbers could be noisy. The second, we said the data is complex. That is, it may not be simple numbers, but images or sound bites or things like that, or non-integer text data. We call it categorical data, like blue, green, stuff like that. What if the relationship between the input and output is more complex than linear? Like we saw one example of a line that we drew. Okay, what if that relationship is more complex? Let's say I have a bunch of points here. Now, how do I establish a relationship between these points? Okay, it's not, definitely you cannot draw a single straight line that fits all these points. Maybe you require something far more complex than that. You require a curve, maybe a higher order polynomial. Okay, so in this case, probably, this 8th order polynomial or 9th order polynomial might fit it. But is that the right thing to do? There are several questions to be answered there. Okay, so that's one of the issues. Even if I am able to represent your input data X as some feature vector, I'm still unable to learn the model, because the set of models possible in our brain, when we talked about those sequences, we had a few sequences, few models. We just tested it, and after that we said, give up. I don't know what the sequence is. But you cannot do that like that, machine learning like that. You need to be able to fit whatever model, and you'll have a large set of models possible. So we need to figure out what to do. Okay. Also, what if your prediction is not a number, like in the case of a cat or a dog? Okay, you have a bunch of points. Your prediction is not a number, it's a cat or a dog. And what if the relationship between these two is also not linear? So you don't have a line that can separate cats and dogs here. You probably require some complex curve to separate out the set of cats and set of dogs. I have plotted these as points in some 2D space. Okay, just as an example. Fine. So what is the solution at the end? The solution is that we're going to convert everything into numbers. So whatever data that we get, whether it is actual numbers itself, or if it's categorical data, or if it is images or sound or whatever thing that is going to come to us, we're going to convert everything to some numbers. And not just any set of numbers, it will be a vector of numbers. Okay, we convert everything to a vector of real numbers, and that would be our input feature vector, we call it, that is X. We convert all predictions also into numbers, into an integer or a real number. If it's a classification problem like cat or a dog, I'll call as cat as 0, dog as 1, or vice versa. It doesn't matter what you call it. So that way you can convert your labels also into numbers. If it's a real number to be predicted, of course, it's already a real number, so we don't have to worry about it. In the case of this one, X, it will become points in a feature space. So if it's a d-dimensional data, a vector, you can think of it as a d-dimensional point in a d-dimensional feature space. Now, given all this, what is our problem? What is the problem of machine learning? The problem of machine learning says, I'm going to give you a bunch of examples. Let's say n examples of pairs of X and Y. Remember, X is already a vector. So when I say Xi, I am saying the ith example. Okay. So let's say the ith image of a cat, from which I've already extracted this nice vector, that is X. So I have a vector X corresponding to a cat, and the output Yi, which says either cat or dog, 0 or 1. Okay, that's a pair. And you're given multiple such examples. So here is a cat, here is a cat, here is a cat, this is a dog, this is a dog, this is a dog. A bunch of examples with X vector given and the corresponding label given. That is given to you. Now, what do you want to do? Our goal is to learn a model Y equal to f of X that captures the pattern of the training samples. So these training examples are given to you, n of them. And I want to be able to get a model fitted to this data in such a way that this y equal to f of x that we learned, the output y of this function f should actually match. That is, if I substitute each of those xi's over here into this x, the function f, then whatever output comes y should be matching with this yi. Okay, or at least closely approximate. Even if it doesn't exactly match, it's okay. It should closely approximate that. Okay, that's why we say it should capture the pattern. It need not be exactly correct all the time, but it should be very close. That is the goal. So our goal of machine learning is this y equal to f of x, learning that function. Okay, and this is a very, very simple and very, very effective understanding of machine learning. That everything that you want to think about, finally everything comes down to y equal to f of x. Okay, we will keep on seeing this again and again and again throughout the course, and at some point it'll hopefully sink into you. Okay, so examples of this y equal to f of x are a line that passes through the points, or maybe more complex curves as we saw. Okay, in practice, many times we'll actually assume a model and learn its parameters. For example, I'll assume that it's a linear function, and then we'll just learn the coefficient vector w of the line. That may be one way. Or I'll assume it's a quadratic function, and then I'll learn the coefficients of the terms. Okay. Once we learn the model, then the second phase is that we can actually predict outputs. So if output y prime corresponding to any new input x prime is possible. So y prime equal to f of x prime is prediction. So once I learn the model y equal to f of x, if a new picture is given to me, I can say whether it's a cat or a dog. Even if I have seen that, even if I've never seen that picture during training phase, it's okay. Okay, this is the high level mathematical simplification of our machine learning problem. That we first take any problem and convert it into this y equal to f of x mapping, where any kind of raw data is there, we'll convert it into a fixed set of numbers called the feature vector x. And any output that we want, whether it is class labels or numbers, whatever it is, I'll convert it into a number, and that I call it as y. And now if I have a bunch of training examples, xi, yi, using those xi, yi, I'll fit a model to it, a line or a curve or whatever it is. And then once I learn that model, I'm done with learning. And then I can go and test myself, go sit in the exam. And in the exam, I'll be given new x primes, new questions, which I have not seen in the classroom. See the connection between human learning and machine learning. You're given a set of examples in the class. You learn a concept in the class. You go sit in an exam. You're given new questions, which follow the same pattern as what was done in the class, but not exactly the same questions. And you will write the output y prime. And if I get most of the answers right in an exam, Astika, please mute your microphones. If you get most of the answers right in the exam, then you pass, which means your faculty assumes that you have learned the concept. Hopefully you have. And that is the only indication I have. I don't know whether you have learned or not really. The only thing I can say is that when I provided you with questions which were not discussed in the class, you got the answers right, which means you should have learned something. And this is precisely what we talk about in case of machine learning also. We give a bunch of examples to the machine learning algorithm. It will learn a model. Then later on, we'll supply quizzes, exams, tests. Test examples will be given to you. We'll check if the answers are right or not. If the answers are right, I'll assume that the machine learning model has actually learned. Okay. So in fact, machine learning has a lot more to do with human learning than many other problem solving. Okay. So let's try to do that comparison now. What is programming and what is machine learning? In the case of programming, it's a very, very simplistic picture, but it's actually quite useful to understand. In the case of machine learning, you have data. Sorry, in the case of programming, you write a program. You provide input data to the program, and the computer will run the program with the data, and out comes an output. Okay, so you provided the program, you provided the data, the computer just ran the program on the data, and out comes the output. Fine. But in the case of machine learning, this is not how we solve problems. Here, what you do, you actually solve the problem and wrote the program. You had to do all the hard work. Okay. In machine learning, what we want to do is, we don't want to write the program. we want the computer to learn the program. F of X is your program. Okay. So what do we do in machine learning? You give examples of data and output. Remember XY pairs, XI, YI. Those were the data here and the output on the right side. We are going to learn the mapping between these two, which is F of X, which is nothing but your program. Okay. So the first phase of machine learning, which we call as the learning phase or training phase, is when we give inputs and outputs to the computer, and the computer will learn the program. It will create the program by itself. You don't code it up. Okay. You just provide X and Y pairs of input output, and the machine will learn the program. And then later on, during the testing or the inference phase, this works very similar to your regular programming, where you provide data, new data there, the same program that was learned in the previous phase goes in, and the computer will run X with F of X and out comes Y. So the second part of it, if you look at it, looks very similar to your programming. That is the process of testing or inference is same before, except that the program that is supposed to be given there was actually learned from the training phase. Okay. So this is the high level picture of machine learning. We have talked a lot. We learned a few concepts now. How do we model machine learning and what are the primary components of it? X, Y, and F, the three things that we talked about. And how do they relate to each other? How does this relate to regular programming? How does this relate to machine learning? How does this relate to human learning? Okay, we talked about all that. Fine. We already talked about what is the relationship between this and human learning. Fine. So that is kind of a very high level overview of machine learning. A bit of simplification maybe, but quite useful simplification. So I'll stop here for a break. Any questions here? We'll take up that and then we'll move on to the next part. Questions? Okay, so the first question comes from Akash Srivastava. Ask, how do we know whether the data is linear or non-linear without plotting on a graph? It's a good question. The corollary to that question is, how do we even plot something which is not even two-dimensional? Okay, so you cannot really plot anything that is more than 2 dimensions. So how do we do this? Well, mathematically, the way we say is that we try to approximate it and see how good the approximation is. So we try to learn with a linear model. You try to fit a line to the data and ask the question, how far away are, after getting the best fit between X and Y from the training data, you ask the question, how far away the points are from the line. If all the points are falling on the line or very close to the line, that's a good fit. And we say, yeah, it's a linear model. It's a linear process that is going on underneath it. But otherwise, it's not a good fit and you will have to look for more complex models. Of course, there are some things that you need to consider, like many times you have issues like noise in the data. So I said the points could be slightly perturbed. So points may not be on the line. That's okay. That we can deal with from the fact that you are asking the question, how far away on an average, what's the distance from the point to the line. But sometimes it could be even worse, that sometimes when somebody typed in, they accidentally pressed an extra character or an extra digit, and suddenly the point should have been here, suddenly it appears in far away from the plot. So then if I try to fit linear models to it, it doesn't work. So there are things called outliers, which you need to kind of ignore when you compute how good a fit it is. So other than that, yes, it is basically just fit the model and see how good the fit is. Okay. Any other questions? Okay. Vinita is asking, using machine learning algorithms, how the scores in the matches are live streamed. I'm not sure what exactly you are talking to. There are several possibilities of this thing that is coming to mind, but Vinita, can you please maybe unmute and ask the question? What do you mean by scores are live streamed? What would be the data like inputs? Okay, so I'm not sure what you mean by live streaming of scores. I don't know whether they are actually done using machine learning, where it automatically extracts the score from some video feed, or is it actually manually entered? That I don't know. But if we are assuming that it is automatically captured, then there are several possibilities. We at IIIT have been working on sports analytics quite a lot. We have developed some solutions with our VR next doors where I'm sitting. It's about a couple of 100 meters from here is Gopi Chand Academy, where a lot of badminton stars, including the big ones that you might remember. So we have worked with them in trying to automatically understand badminton matches. So if I put a camera, we put a camera where the badminton court is, and as the game is progressing, we can actually use machine learning models to detect the people, detect what is happening, and automatically figure out who won the rally. And not only just that, you can also look at the video and make much more deeper analytics into it. How much did the people move? What was the kind of shot played? How many back and forth happened? And all kinds of things could be automatically computed from the video sequence. And using that, you can actually also produce the score of the match. At every point, you know what the score is. So this is something that is doable, and it is possible to actually watch a game and do that. We also did some work on automatic commentary. Can you actually take a live telecasting feed of a cricket match and say what can you generate commentary? You know, who is playing, what kind of shot they played, whether they got out or not, whether it was a 4 or a 6, all those kind of things. You know, can you automatically learn from or do it from the video feed? So there are several things that are possible. So in the first case, in both cases, the input is just the video feed, and you kind of chop the video into appropriate parts and then try to extract some features from inside the video and figure out what happened inside it. Okay, and you need large amount of training data for this purpose. So we will definitely get into examples of that later.
Can I ask a question?
Prince, go ahead.
In case of overfitting, like how do one model something that understand it is like now enough, like I've modeled enough?
So we did not get into overfitting and underfitting and stuff like that. We will talk about it probably later. But yeah, it is an issue that if you have several models that are of varying degrees of power, so linear is the simplest, maybe quadratic, cubic, you can think of more and more complex models. The question is, when do we stop? At what point we say, yeah, that's good enough fit? Or do we actually go for even higher powerful models and try to exactly fit the training data? Many times it's actually not a good idea to exactly fit the training data. Okay. When you're sitting in a class like this, or even in a real classroom, it's not a good idea to learn to kind of believe every single word that is coming out of my mouth. You know, I might be speaking, I might be stuttering, I might be, you know, like this, holding off and then trying to say something. I might say some sentences, go back and correct the last few words that I spoke without actually explicitly saying that. I don't say that, okay, I speak a sentence and I stop and say that erase the last 3 words that I said, go back and start again. I don't do that. I just stop and then restart. And you kind of know that, oh, I'm actually speaking over the last few words that I spoke. So there's a lot of cleaning up and processing going on in your brain when you see the data. So you don't want to overfit to what I'm speaking. You don't want to exactly believe what I'm saying. You need to kind of approximately understand this and also simplify your understanding. So there is this, in some sense, it's a dilemma, how complex a model you want to make, but it's also extremely relevant to learning. If you use a powerful enough model, you can fit any data that you want. Let's just take a human example of it to understand it. Assume you have supernatural or superhuman memory. Okay. If you have superhuman memory, you can by heart every single question and answer in the world. And then if I ask you a question, you will immediately give the answer. Does that mean that you have understood the concepts? Even if you can memorize every single, question and answer pair, that does not mean that you really understand it. You just committed it to your memory and you're just retrieving it. That doesn't really help. That we don't even call it learning. So you need to kind of simplify things. If it is too complex, you want to be able to explain whatever you've heard using some simple models, like line is a simple model. Maybe quadratic is also a simple model. Depending on the situation, you might want to use something that is relatively simple. And if you have multiple models possible, and one of them is a simpler one, which is almost correctly explaining everything, then that may be the better one. So there is something to be said about simplicity of the model and learning. In fact, you can say that learning is simplifying. Okay. So I used to say this, that when I was younger, that I'm dumb. I need to simplify things down before I can say that I understood. And later on, when I learned machine learning, I understood that what I'm saying is right. If I don't simplify it, it's not even learning. So the fact that I need to simplify things sufficiently low that I need to be able to understand it means that I'm actually learning it better. Of course, it takes more time to learn. I might be a slow learner. That doesn't matter. If you are able to simplify things better, then you're actually learning better. So simple models are always preferred over complex models. And it's not necessary that you fit every single training sample exactly. As long as you can do well in the exams, which is during the testing phase, you're good. That is what the important factor is. Okay. So now there are a bunch of questions in the meanwhile. Let me quickly go over it, and then let's get back to the lectures. So how Venkatesh is asking how machine learning models build the program itself for the given input data and output data. So that's in our example, our f of x that we talked about, that is the model, that is the program. So if y equal to f of x, if f of x is a linear function, then what do you learn? You learn the coefficients of the line, w1, w2, w3, and w0, the coefficients of the line. That's what you learn. And once you have it, that's your program. The next input comes, you plug it into the equation of the line, and out comes the output. That's all. In the case of simple linear functions, that's all what you're doing. Vinita is asking, I think that is already answered. Akash Srivastava is asking, in case of categorical data, how do we convert them into quantitative data? With not very good, nice answers right now. We will talk about much better solutions later on. But right now, the crudest way also is okay, which is just assign some numbers to it. If I have red, green, blue, yellow, purple, a bunch of colors, just call them 0, 1, 2, 3. That's it. Each category is randomly assigned a number, usually a sequence. You order the categories in some order. If you cannot order it, that's fine. Just put it in whatever order you want and just call it as 0, 1, 2, 3. That's it. So right now, that is the solution, which works in surprisingly well in many cases, but we'll go for better solutions later on. Okay. Devdatta Chatterjee is asking, if we supply all the data for learning the model, how can we know if the model fits the data if new data is provided? Because we don't know the answer as human. That's a problem. So if you have a bunch of training data, you have a bunch of data for which you know the answer. If you supply everything to the algorithm to learn, you cannot test it. For testing, you require some data for which you know the answer. Then only you can look at it and say that, yeah, if this input is given, is the output correct or not? So you need to hold back something. Okay. Always, if you have a bunch of data with you, you hold back some percentage of it for testing. Only the remaining you will get for training. Janardhan Rao is asking, in testing inference, what type of data X prime will we give as input for a computer? It's the same kind of thing. If during training, whatever method was used to convert raw data into a feature vector X, the same process would be done for testing data also. So if the input was a picture and the output was cat or dog, you did extract some numbers out of it. Whatever technique that you used to extract those numbers during training, same thing would be done for testing. How modern machine learning differ from machine learning? Well, I would, the several answers that you can give, but let me take that answer a little later. Let me talk about the next part of the lecture, and then I'll give an answer to that. Okay. How can we convert all kind of input data and predictions into integer real number? That's part of the next section. Okay, let's get into that. How do we convert images into real numbers? All those things we are going to discuss right now. How machines will work on given data. We talked about it now. You have a vector X, you have an output Y. You need to find the relationship between that. You need to fit a model to it. What is the process of model fitting? That's the rest of the course. Okay, we'll dive much deeper into it. Is there an alternative for data conversion instead of vector of real numbers? There are other ways also. Okay, as of now, we will use the idea that any kind of raw data that you get, you're going to convert to a vector of real numbers. There are other kind of conversions as well. We will discuss that when the time arises. In some cases, for example, we don't convert categorical data into real numbers. We just keep it as categorical data. Okay. We don't treat them as real numbers. We just consider them as categories. And in some cases, you might have things like, sequence of numbers which are not fixed length. Like I speak a word and you want to understand. The length of the word that I speak would be different. The same word if I speak. Let's say I'm speaking the word computer. I can say computer. I can say computer in a slower manner, or I can say quickly computer. And all these are supposed to map to the same answer, which is I spoke the word computer. So how do I convert that? Because every time I speak, it will have a different length. And if I take the waveform, it will be of different length. And that would be a problem. So how do you deal with this kind of variable length data is a question. Okay. So yeah, whole bunch of questions yet to be answered, but we will slowly cover that one by one. Okay. Last question from Hafina. In machines, data already set or not to solve the given input data? I'm not sure, Hafina. I did not understand your question fully. If you could explain that. In machines, data already set or not to solve the given input data. So I believe what you ask us is the data already present in the machines to solve the mapping from input to output. That's part of the learning process. So during the learning phase, you supply the data. So there is a learning algorithm sitting there. You supply data to it in the form of XY pairs, where X is a vector and Y is a number. You provide that. That's part of the input. So data sets, data sets would be part of the input to the learning phase. Once that is done, once the learning phase is done, the machine learning algorithm, the learning algorithm would have distilled all the information from that data into a model, whether it's a linear model or quadratic model, whatever it is, it would have created that. Then it needs to only keep the model. During the inference phase, all you need is that model. You get an input, you can create the output. Okay. So let's actually get into that. Okay. So we will discuss that. All these things, what I just said, is actually part of the next part of the talk. So let's get into the second part of the lecture. What is this machine learning? This is exactly what we were trying to speak. Okay. So the machine learning process is this. You have a bunch of training data, XY pairs. Okay. That is given to you. This could be raw data. If it is raw data, first I need to extract some numbers out of it. And this process, you call it as feature extraction. So you take each pair of X, Y from the X or whatever input raw data that is corresponding to X, you will extract those numbers. Okay. And that would give you a feature vector for the X, and Y you already have Y. Okay. Whether it is cat or dog, or is it actually a number, whatever it is, that's your Y. So given pairs of input data, you will extract features from the raw data. That's the first process, feature extraction. Once you extract the features, you can think of those vectors, the vectors X, as points in a d-dimensional feature space. If it's a d-dimensional vector, you can think of it as a point in a d-dimensional space. And since what you put inside those space is feature vectors, we call the space as feature space. Nothing fancy about it. It's just a space, Euclidean space. Okay, 3-dimensional, 4-dimensional space, whatever it is, we just call it feature space because everything inside it are feature vectors. So you have a bunch of points in a feature vector, that in a feature space, that is the representation. Fine. Now you need to learn the classifier or whatever your machine learning is. So classification is one such problem. Classifying between cats and dogs, for example, is one such problem. And you need to learn the classifier. So the classifier design is the learning part, where you will try with different models, try to fit different things, whatever fits the best in whatever definition of best it is. That would be the learning process. We will get into details of all of these things. Okay. So I'm just trying to give you the high level overview. We will dig deeper. And what comes out as a output of this learning phase is the classifier model, which is the parameters of the model. Usually a line has got coefficients for the each of the feature vector values, and that would be your classifier model. Okay, this is the training phase. Training data, feature extraction, and outcomes XY pairs where X is a vector. Then you apply your learning algorithm on top of it. You will get a classifier model or a regression model. If you're talking about mapping numbers, it's the process called regression. We will talk again about it later. Okay, so whatever machine learning you want to do, output is a model. Then what happens during testing phase? During testing phase, again, you have test data, but this time you don't have labels for it. If you have labels, you don't give it to the machine, you keep it to yourselves. Okay, you're running a test. If you're running an exam, you don't give the answers to the students. You only give the question paper. And when the answer paper comes, then you match it with the correct answers, isn't it? So in the test data, you only provide the questions first, which is the raw data. Again, you do feature extraction. This becomes point in a feature space. Now you have a points in a feature space and the classifier model. I can match the two. I can plug in the X prime, the point that I got from the feature extraction, into the classifier model. And that process is called classification, or this thing. And out comes the label. And this class label that comes out will be matched with. So if you are the person who is running the test, setting the question paper, the answer paper is your answer paper is the class label. You match that answer paper with the correct answer that you have. And if it matches, good. Otherwise not. And you do this over a large number of test examples. And based on the accuracy, you decide how well the learning algorithm performed. Okay. See the equivalence with this and human learning. Okay. The top thing that you see on the top here, from training data all the way up till classifier model, is your classroom training. And this is your exam hall. Okay. Oops, sorry. So now let's actually take some examples of this feature extraction. This is the next problem that we talked about. Okay. Once again, keep your microphones muted unless you want to ask a question. I think MS, you're trying to ask a question. Your audio is not clear at all. If you're asking a question, I'm unable to hear you. Can you please type the question? Okay, I'll pick up the question whenever it appears, if you have one. Okay, so now the problem is that of feature extraction. That is the main focus of this part. So let's take a simple example. And I want to classify between apples and oranges. Okay, apples and oranges are two different fruits and I want to separate. Given a fruit, I want to be able to figure out whether this is an apple or an orange. So the question is, what kind of features can you extract? Okay. So again, a question to all of you. What do you think is a number that I can extract from a fruit, which will be, one number or some kind of numbers for apples, but a different kind of numbers for oranges. So here things like color, size, RGB value, stem. Yeah. So there are several things that are possible: color, shape, texture, the skin surface, however it looks. Sometimes the orange seems to be a bit more rough. Apples seem to be a bit more shiny. Okay. Yeah. Again, whole bunch of things. Just like the cat and dog example, there are several things possible. So let's take two simple ones from what you said. The first one is color, but then, orange is orange, some sense. But of course, from the examples, you can see that there are oranges that are not orange in color, but apples also usually red, but then there are yellow apples, green apples, depending on whether it is ripe or not. You will have different colors, all those things. So now, how do I extract a color out of it? Okay. So let's think about extracting two numbers so that I can plot it in a two-dimensional feature space here. So I want a two-dimensional feature space, feature representation, and I want to get two numbers out of it. First one, from the examples that you gave, color is a good example. So the question is, how do you represent color? Somebody said RGB, but then RGB is three numbers. Let's take one number, and for argument's sake, let's assume that oranges are a bit more red than, apples are a bit more red than oranges. Okay, so more red means apple, less red means orange. Let's just, that looks like the overall trend. That's not exactly true, but that's okay. So now, since that factor exists, that the fact that apples are more reddish than oranges in general, we can hope that, redness, instead of just saying color, redness may be a good feature that I can extract. And if I have RGB values, you have R, G, and B, you just pull out the R from the pixel. Ignore the B, G, and B, just pull out the R from it and see how well it works. Or you can do some ratio of R to G and B, and based on that, you can decide how red it is. Pick that out. So the first feature that I can use here is color, specifically redness. Okay. Now the second one, several suggestions came: shape, size, all kinds of things. But then size of it actually depends on how zoomed in or zoomed out your picture is. That is difficult to answer. Texture, as Rishi says, is one possibility. Problem is, how do you define texture? We will do all that later. Okay. But right now we want simple answers. So several possibilities are there. So size is one possibility. Maybe apples are bigger than oranges, or other way. The top and bottom of apples are dimpled a bit. So if I can detect that dimple, that's one possibility. There is different ways to do that. But let's take something simple. I just want to, put into you a fact that not every feature needs to come from the same raw data. So if you have images of apples and oranges, color, redness, many other things you can extract out of it. But in a practical classification problem, maybe you have other sensors as well. So maybe there is another sensor which can measure the shininess of the surface. Okay. Maybe there is a simple sensor, a weight sensor sitting underneath it, which will give you a digital reading as to what the weight in gram is. So feature vector need not necessarily come from a single raw data. If there are multiple sensors, it is possible that you can extract, numbers from different sources and then put all things together into a vector. So let's put one from weight. So I'm going to use weight as the second class. And now the question is, can I convert every one of these fruit examples into a feature vector of 2 dimensions? So I'll take one fruit, let's say take the top apple here. I will measure its redness. It is pretty red. So maybe the color of that particular one, CI, is pretty large. Second one, I may measure its weight. It's not very big. So maybe medium weight. So if I have these two things measured, then what happens? This fruit image and the corresponding weight together forms a point in a 3-dimensional space. Sorry, 2-dimensional space. So that apple becomes a point here. I'm going to put red color for apples, and I'll use a different color for oranges. Okay, maybe green for oranges. And similarly, I take another fruit, yellow apple here. This is heavier. So in the weight axis, it might be to the right, but in the redness axis, it might be lower down because it is not very red. This one, it is even less red, but maybe slightly bigger than the previous somewhere in between the previous two apples. Okay, I'm roughly putting these in some appropriate place here. Okay, this is not exactly computed input. And similarly for all the other apples I can do. Okay, and then I do the similar things with oranges. This particular orange, it is okay, a bit red maybe, but weight wise it is very small, so it may be very low in that weight axis. And similarly others I do. So I end up putting all these fruits into the space. So now I have a feature space representation for every one of these fruits. Fine. Now, what is the model? Model is, I want to classify here. I want to separate apples from oranges. And once again, we'll stick with our simplest model that we know, which is a linear boundary, which separates apples and oranges, a line that separates apples and oranges. Now, can I draw a line that would separate all the red points from the green points here? Doesn't look like. Whichever line I think about, it will always put something wrong. So I'll go back to my statement saying that it need not perfectly fit the training data. As long as it approximately does that, it's fine. So I'll take a simple line. It almost classifies everything. It gets one apple wrong and one orange wrong. Everything else it gets right. Okay. I might be able to find a very complex curve that actually separate all the red from the green, but then that may not be the best answer. Okay. Maybe these two apples and oranges were either mislabeled. Somebody when they entered the label, they wrongly labeled it, or it could be that they are exceptions. You know, some apple was stunted in growth and hence its weight was low and it became, moved into the feature space area of the orange maybe. So all those kind of things could happen. So as Divyansh points out here, it could be considered as outliers. Okay. So it's okay to make a couple of errors in the training data. As long as we get most of the test data fine, that's good. Okay. So in the same picture that we talked about, the training data contained apples and oranges and the corresponding labels. We extracted the feature vector, which was weight and redness. It became points in a 2D space. The classifier design was finding the line that's separating the two, and the classifier model is the equation of the line. Okay. Finally, we end up with the equation of the line. You don't require to keep all the training data after this. You only need to keep the equation of the line. Okay. During the testing phase, same thing happened. An unknown fruit is given, which is either apple or orange. We extract the features. You get a 2D point. You substitute this 2D point on the equation of the line. Point versus line is substituting the equation of the point in the line. And if it is on one side of the line, you will get apple. On the other side of the line, it's orange. Okay. So that's the class label. By the way, I hope you remember the equation of the line. If you substitute on one side of the line, you get a positive number. On the other side, you get a negative number. Okay. Devdatta is asking, should the features be linearly independent? Not necessary. Okay. It's not a necessity that the features have to be independent to be able for this to work. Is data always linearly separable if we are able to find the correct space to transform into? Okay, that's a more deeper question. Can you always separate everything with a line? Of course not. But if you are able to kind of take the feature space and warp it, can we actually twist the feature space in a meaningful fashion so that the points become linearly separable after that? Can you actually always draw a line that separates? To some extent, yes. Okay, and that's a whole different part of machine learning, which we'll talk about in detail in one of the modules is fully dedicated to that kind of things. Okay. The other question is, can we learn what features are good through a model? And that is the answer to your previous question. What is the difference between machine learning and modern machine learning? The fundamental difference between machine learning and modern machine learning is that you have started learning features now. Okay. Up till then, people used to handcraft the features, just like what we did, weight, redness, all those kinds we used to extract, and we used to do things. but now we have started to learn features, and that is what made all the difference. Okay, we will talk a lot about that, of course. So some simple examples. If the input is sound, like a word, how do we represent it? Maybe the amplitude and frequencies can be measured, and that could form the numbers. Or you could do something more complex, like, if you have done your signal processing, then wavelets, coefficients of those wavelets that can fit it, MFCC are examples of that. Images are given to you. What can you do? Well, you need to extract some kind of numbers that would capture the shape, size, color, or texture, or some property of the objects. Okay. Slightly better ones, there are practical examples where things like statistics of gradients of images are used, where you compute the derivative at every single pixel and then do some kind of histogramming of that. And that would become a good set of numbers that can describe objects. If it is text, well, you can do things like statistics of characters or words, which you will actually play around with in the lab sessions today or during the week. How can you extract features out of text? So you can do things like, frequencies of occurrence of characters or words and stuff like that. That is one possibility. Interesting question is, can we actually extract some numbers that capture meaning of words? Is there a way in which I can extract a number out of a word which actually has some relationship with its actual inherent meaning, not the characters present in it? And that is definitely one whole area that we will get into later. Okay. Somebody mentioned embeddings. That's one term that is related to it. What about videos? Well, we can do things like, tracks of objects. If an object is moving in a video, can I have a 2D sequence of points that follow the object? That's maybe one kind of feature. Several other things that are possible with it. Okay, so this is the process of feature extraction. I just gave you a quick introduction. We will, again, with specific examples, specific problems, we'll learn new kind of features that can be extracted and how that can be used for learning. Fine. So any questions regarding feature extraction or the process of classification? What is training? What is testing? What goes into the training process? What comes out of the training process? What goes into the testing process? What comes out of the testing process? All those things, I hope it's clear. If you have any questions, we should clarify that and then move forward. I think I have covered most of the important technical parts now. I just talk a little bit about machine learning after this general story, and then we'll move forward. Are there any scenarios where extraction is impossible? If sensing is possible, then there should be some way to extract numbers out of it. How good the numbers are, that could be a question. It need not be. There may be cases in which you cannot get a feature vector that is good enough for us. That is possible. But not being able to extract itself is not necessarily happening, because if anytime you can sense anything, if you have a sensor which would capture something about the object, it is already numbers. Remember, image is not really image. Image is a bunch of numbers already. So for computers, it's not very difficult. It's just converting one set of numbers into another set of numbers. How good it is the more important question. Okay. I haven't worked on sound, so what are usually features for any audio? So we will talk about that, Gokul. Sound is nothing but a sequence of amplitudes measured in the waveform. So once I have a sequence, there are several things you can do. Typically, you take small windows of it, you convert it from time domain to frequency domain, and then from frequency domain you get some numbers. That's the simple answer, but we will actually go through that. Is there a feedback step to present ML models, like after making an inference? That is, if you are doing any feedback and you are using the feedback to improve your learning, then that is, again, that becomes part of your learning process. So there are several learning algorithms in which you will learn something. You use some of the quote unquote test data. That's not really test data. Now at that point, we call it validation data. So you learn something, you try take a mock test, see how it works, come back and update your learning, take another mock test, remember your entrance test. You used to learn, you used to take mock tests, come back and learn again, take mock test. And after doing this several times, once you're confident, you go back and write the real exam. Okay. Same thing can happen in machine learning. You have training data. Mock test is basically on mock test data, which is also called validation data. So you do training, you do validation, training, validation, keep doing this a lot of time, and then finally go and take the real entrance exam, which is the real test. After converting frequency to frequency domain and getting some statistics, is it still time series data in the case of sound? It may or may not be. So you have both ways of doing it. You can convert the whole thing into frequency domain and no time series information is, no time sequence is presented anymore. That is one possibility. Or you can actually take windows, small windows of it. I take one window, extract the frequencies in it, take another window after a bit of time and then extract. So you have basically a sequence of frequencies. So there is some time information present. So both kind of things are possible. After converting, okay, I think Hafeen is asking, why have you chosen weight instead of so many features? Just as an example, I just wanted to put into your mind saying that not every feature need to come from the same sensor. Otherwise, yeah, anything is possible. Something simple is what I wanted. Can ML models help in extrapolating data? For instance, if you have limited experimental data for a particular temperatures and want to extrapolate, you can, but anytime extrapolation is always have to be put with caveats that once you go outside the domain of your learning, beyond the domain, beyond the boundaries of the learned domain, then things get less and less sure. Okay. So yes, it is possible. Interpolation is easier. In some sense, interpolation is what you do all the time. Learning also involves interpolation. Model fitting is interpolation. Extrapolation you can do. Once you fit a model, you can also extrapolate, but your confidence usually in extrapolated regions are less compared to interpolated regions. GAN models, we'll get into all that later. Okay, that's too complex for now. How can we measure the confidence in that case? Good question. Let's actually get into probability, confidence, and then we will really talk about these things, Gokul. Okay. Fine, let's move forward. We are running out of time. So let's just see some examples in real world and how the real world problems map to y equal to f of x. And this is really what you are supposed to do from now onwards, throughout the course, throughout the year, while you are learning this course. One thing that you should learn is how to take a real world problem and map it into y equal to f of x. Okay. If you do it the right way, there are better solutions that will come out. So this is something that only comes from experience. So I'm just going to tell you a few examples and then see if, as you walk around from now onwards, when you're walking on the streets, when you're watching out through the window, whatever it is, or you're sitting at home doing something, every time you see a real problem in the world, see if it can be modeled as a machine learning problem. If you can actually capture it as a machine learning problem, or in other words, if you can convert it into some simple y equal to f of x, then you know how to solve it. And this is an art more than science. The ability to look at a real world problem and be able to pose the right kind of machine learning problem inside it will decide whether you can actually solve it or not using ML. Okay. So let's see some simple examples first. Autonomous navigation. Now you have a car which is fitted with a whole bunch of sensors, and this is posed as a machine learning problem, how to drive the car. Okay, you have some inputs coming through the cameras and lidars and all that, and output is whatever that the driver is supposed to do. The driver is supposed to steer, brake, acceleration, all that. That would be your output. Okay, if you can do that, then you're done. Your car will drive. Okay, as simple as that. Second example, let's say personal assistance. Sound inputs come into this one. There are microphones that would capture it, and you have to convert this sound sequence into questions or instructions. Then you need to understand it. Then you need to find the answer to it, and then finally convert the answer back to audio and then play through the speakers of it. So it's basically raw data, which is sound, gets converted to a bunch of numbers, which gets converted to other set of numbers, and then finally it will be matched with solutions, and the solutions again will be converted to another sequence of numbers which actually represent sounds, and that will be played through the speaker. So there's a whole bunch of conversions going on. Okay, we'll again get into more details of each of these steps later. Now machine learning solutions are also doing things like automatic generation of new data, creativity, new kinds of images being created, faces that are being generated which has never been there before. All these pictures are all faces of people who don't even exist in the world, who never existed in the world. They are just imaginations of your machine learning algorithm. So there the input is just random numbers and the output becomes some kind of a face. Okay. Of course, things like machine learning models playing chess or Go and stuff like that. The input is the board position right now, and the output is what move to make next. Okay, again, learned through machine learning. So we already talked about, to solve the problem of autonomous navigation. What is the features that you should use here? Well, if you look into this picture, what to do depends on the road condition, the boundaries of the road, where the traffic in front is, how much curvature is there to the road. Based on all that, you need to decide whether to speed up, slow down, turn, move to the left, move to the right. All those things you need to decide. And you need to be able to extract features that can tell you whether the road is straight or curved, whether there is a car in front of you or not. If there's a car, how far away it is. Are you to the left of the lane or right of the lane or in the middle of the lane? All these things you need to be able to extract. Okay, so you can sit down and hand code these features. That's one possibility. Or you can let the machine learn automatically. That is what modern machine learning, deep learning is all about. And another important factor is to be able to ignore things that are not relevant, like the trees on the left up there. Doesn't matter what is up there. You only are worried about the road and things around the road. So you need to be able to extract some features. I'm just showing some pictures of features that are extracted by modern machine learning. You extract numbers like these and then use these to finally decide what action to take. And what are the actions here? Turn left, turn right. If so, by how much? So you're steering how much you want to turn left or right. And the second is how much you want to move forward or backward, accelerate or decelerate. That's basically all that is there to driving. Okay. So what is this nature of y equal to f of x? Of course, this is the image from which you will extract some numbers in the middle here. And that would be your x vector. And your mapping from x to y would be slightly complex. Okay. If you have 4, or in this case, 2 outputs to be generated. One is the steering position. Let's say it goes from -1 to +1. Okay, some real number between -1 and +1. -1 means turn left, +1 means turn right, fully right and fully left, and you can do anything in between. 0 means go straight. So that is one number to be generated. Second number to be generated is whether to accelerate or decelerate. So let's say that's also a number between +1 and -1. +1 means full acceleration, -1 means complete brake, the hardest braking, and other numbers in between. Okay, so you just need to generate 2 numbers. That's all to autonomous navigation. Okay, given this input, if you can generate those 2 numbers correctly, you can drive from anywhere to anywhere. So you've already converted your problem into y equal to f of x. Where there are 2 outputs, we can think of it as 2 different functions. One function controlling the steering and another function controlling the brake and accelerator. Okay, that's it. That's all there is to machine learning. This is how you map from a real problem into appropriate feature extraction into an appropriate y equal to f of x. It could be 1 or 2 functions, or you can also think of y as a vector, where there are 2 numbers in y, and that's what it will output. What are the challenges in it? You can think of enough number of challenges. Okay. So if you look at modern machine learning, the fields that are impacted by modern machine learning the most are natural language processing, computer vision, speech processing, robotics, and so on. All these are examples of cases where the input is usually high dimensional and the input is raw and input contains a lot of noise. These are the kind of things that used to be very difficult to deal with traditional machine learning, which are now becoming better with modern machine learning. That's because, as I said already, modern machine learning has become better at feature extraction. It has started doing learning of feature extraction, and that's why this is so good. Somebody is asking, who is it? Nagesh asking, is it possible to give more than 2 or more different inputs at the same time? Yeah, any number of inputs. You just concatenate all those things together and that becomes a big vector. That's okay. Why can't the output be a vector? Say, I think I already said that. So you can think of output as a vector, that's fine. And that's one way to think about it. Second way to think about it is if there is a vector output, then it can be thought of as 2 different functions, from the input to the first number and input to the second number in the vector. Both treatments are there. So there are cases in which you will single model you use to learn the vector as output. That is also available. Neural networks and all does that, multiple outputs. There are other methods which only produce one number. In autonomous cars, do we feed the whole feed of driver driving a car, or we choose a specific action to a specific signs like stop signs, footpaths, red light? Both have been tried out. The first autonomous navigation car, which came out of CMU in 1980s or so, 80s, 90s period, there were a lot of self-driving cars that were developed at Carnegie Mellon University. There was one Professor Takio Kanade who was leading the robotics group there, and he spearheaded a series of cars that were built there. They were called Nav Labs, they called it. And it was actually the one that finally worked the best was pretty simple. They had a camera in front, and the camera was a very low resolution camera. It was connected to the image from that was actually converted to even lower resolution and fed into a computer where a simple neural network, we'll talk about neural networks later, a simple neural network was trained. The input X was the image from the camera, the raw image from the camera, which was actually simplified even further. They just integrated the image, summed up the image along the columns in certain fashion. And that was the input, a series of numbers. And what they did is they just attached a sensor to the steering wheel and the brake and accelerator. It was actually, there was no clutch. It was an automatic gear. So just had 2 sensors. One is connected to the steering wheel. The other is connected to the accelerator. And based on those 2, that was the output, ideal output required. So you have the input coming from the camera, the ideal output Y is obtained from these sensors. And then they just asked some of the students to drive around. So the students were driving around in Pittsburgh, and it would learn from the data. Every time an image comes, you know whether the person is turning the steering wheel or braking or accelerating. And that was used to train the neural network, and that was your and it worked. And there was a story when this car drove from New York to Los Angeles, which is kind of both extreme ends of US, and several thousands of miles. It drove by itself in the sense that about 99% of the time it was driving by itself. About 1% of the time human driver had to intervene, okay, which is not very difficult to do. But modern cars have become much better. There are a couple of questions here. Why can't the output be a vector? I think we already said that. In autonomous cars, do we feed the whole? I think I already answered those 2. Okay, so let's just quickly look at a couple more examples, specifically from the field of computer vision here. There are, for each of them, you can give several such examples, but I'm only looking at, just for lack of time, I'm only picking up computer vision from here and trying to see a few examples. This is in the field of medical image processing. Machine learning has been used to do things like, given the scans, X-rays and MRIs of the patients, you can actually overlay the scans. For example, this is an example of a orthopedician trying to fix the broken bones in a person's body, and the computer can actually understand the posture of the person and overlay the broken bone picture on top of this thing, so that the surgeon knows exactly where the bone is and how it is broken, so that the amount of incision required is minimized. This is computer assisted surgery. Then there is, even CT scan that is actually a computer processed version of the data. So you get a whole bunch of integrated images along different axes, and then you need to combine all that to create this 3D model. Image segmentation, automatic segmentation of this thing. This is actually the cross section of your lungs. The two black regions that you see are the two lungs, and the question is, can you actually find the boundary of lungs to the rest of it, so that you can actually measure the lung capacity? If you can do this automatically, then you can objectively measure the lung capacity over multiple, over a period of time, and then see how the patient is responding to certain treatments or exercise or whatever it is. Okay. Another area of machine learning, this is space imaging. Here are examples of a picture taken on top of the Amazon rainforest. Here is the Amazon river here, and the Rio Negro, which is over here, which is joining over here. The color is not real color, it is pseudo color. So red color that you see here is actually vegetation, and the white color that you see in many places is white clouds, but in certain other parts the red color is missing, which is actually deforestation. So you can actually use this image to compute the forest cover in it. So again, think about y equal to f of x here. What is x? It is this image, and whatever feature you want to extract from each portion of the image, and y would be the amount of vegetation or the forest cover, and based on that you can take decisions. Okay. Automated inspection is a very popular one. Manual inspection of especially things like PCBs are very difficult to inspect because there are a whole bunch of lot of small connections, and somebody has to sit down and look through a microscope and decide every single connection is it properly done or not. Whereas machines are much better at it. You just take a picture of a PCB, and it can inspect every single line and make sure that every connection is properly made. Once again, what are the inputs and what are the outputs? Think about it. You'll have each region of the PCB. It'll have the image would be the input, or some features extracted from that would be the input. And the output is for each of those regions, are all the connections good or bad? So 0 or 1 would be the output at every single position. And final output could be that where all there are problems in the PCB can be output as an array if you want to. So that's another example. One more example, let's say in biometrics, you are trying to recognize a person based on their face or iris or fingerprint or hand palm print and stuff like that. Several applications of it in several different domains. All of us have Aadhaar cards, which is using your 10 fingerprints, your 2 irises and your face image. All this is used to decide, to match 2 persons and see if they are the same person or not. And that has several applications in travel, in cases of access control, in tickets and queues in several places. This is a famous example of a person who was photographed when she was very young, 13 years or 14 years age. This girl was in a refugee camp from Afghanistan, and this picture became very, very popular because that kind of captures the hardships that the young girl has gone through in her short life. And later on, the photographer who took this picture, he became very, very famous because of this picture, and he won several awards and stuff like that for it. But he never knew this girl because he just took this picture and during in the refugee camp walked away, and then never even asked the name of the girl. He did not know that this picture will become so famous. And then later on, about 15 years, 20 years back, he went back and tried to identify the same girl. He had to go through a whole bunch of difficulty, but finally, when they found, it was very difficult to figure out if it's the same person or not, because there were several people who were claiming that, oh, I am that person for the hope that they'll get some money. So finally, one of our colleagues, John Dogman from UK, he was able to do the matching of the iris patterns from these two pictures and confirm that yes, they are the same person, and found out the name of the person was Shadab Gul. She is now married and has several children, a couple of children, and living somewhere in Afghanistan. I don't know what the current status is, but this was a few years back. Okay. So basically, again, what is the input output here? The images are inputs, identifying, taking the specific portion of the iris, extracting some numbers from it. That is the feature vector. And then the comparison that you do is a simple matching of the two feature vectors and see how well they match. And the output is a 0 or a 1, depending on how the matching is sufficiently good or bad. You have other applications in TV broadcasting, doing overlays of lines and pictures. This requires detection and understanding of entities inside the image. So there are several applications in that, and you can think of several others beyond this one in surveillance, automated assembly, mail sorting, in face detection. In many of your cameras already have it. Robo navigation, content-based image retrieval, entertainment, and many, many other things. You are the people who should be developing the next generation of these solutions out here. So that's all what I wanted to say. So it's a very high-level introduction to machine learning. We already learned a few concepts. We talked about what the problem of machine learning is, what is learning, what is training, what is testing, what is the process of conversion of raw data into feature vectors, and how do you model the machine learning problem as y equal to f of x, what is the inference time, testing, accuracy, all those kind of things. We kind of touched upon many of these things. We will go deeper into each of them in future. A couple of questions, I would answer that and stop. We are past our time of 1 o'clock. Is it possible to, I think this is already answered. I think these questions were already answered. Any other questions related to this? All good? I hope. Can we get your presentation for reference? As we were saying, Professor Jawahar was mentioning this before. Yes, we will make our presentations available. That's not a problem at all. But remember, none of this is just, your process of sitting in a class, going through this and understanding is good, but you need to do the work after this. So Tripti is here. She'll talk about the labs afterwards, and that is the most important part. All the lectures and materials and whatever we provide is as a mechanism for you to be able to do the labs and the projects, because the learning is really when you do those things. When you do the assignments, when you do the labs, when you do the projects, that's when you are actually able to both learn and also develop the confidence that you can do things. Okay, so that is sure. I mean, for reference, definitely we are going to give you the slides. We will upload it in the learning portal. You can take it from there. I'm sure the videos of these classes are also available. Can we do real industry-based projects in this course? Yes, we will be doing real-world projects, but remember, there is a trade-off between taking up real-world problems and taking up problems which will best support your learning. If I take a really complex problem, you can't even start to attempt it without knowing a whole bunch of things. So when you start in the learning process, you will take simpler problems, real-world problems, sure, but simple problems, so that we will kind of mask a whole bunch of issues and try to learn one or two aspects of it. Then as you move forward, we'll make the problems more and more complex. Okay, so sure, you will be doing several projects and problems and labs and assignments which would be significant enough that you can think of them as solutions that can be deployed in real world with appropriate modifications and testing. Okay, so good. We'll stop over here. Tripti, you want to take over? Thank you, and I'll see you again sometime next week or the week after. Okay.
Thank you, sir. I have a few announcements to make. The first is that we are creating a Discord channel for future communication, and the link will be sent to all the participants via mail. So please join the Discord channel. That will facilitate communication between the participants and the TAs, and we can make announcements there. It will be a one-stop place for all this. We will update the first lab. So every class has an associated lab with it. So today was the first class, so that has an associated lab with it. And we will be updating the link for that lab in the Discord channel once it's created and once we give the link to you. So what you can do with it is, the labs will be in the form of collab notebooks, and you can run the code in the collab notebooks, and there may be some extra questions where you can explore some things. So you can do that, and we will let you know the method of getting back to us with these labs. The participants will be divided into a few groups or houses, and there'll be separate TAs for each houses. So if you want to get back to us with any doubts or questions or any issues, then the way of communication will be through the TAs of your respective house. We will be creating separate channels for these. So this is to, since there are so many participants, this is to streamline the communication. So don't worry about all this. We will be doing all this in the Discord channel. So the lab will be given to you today or tomorrow. So please go through it and try out new experiments. And by the end of this week, you can get back to us with the lab. So